So good morning, everyone. Welcome to the second day of this program. So we have our first talk by Hio from Yale University. She's going to talk about invariant measures for horospherical flows. Since it's a Zoom section, I request you to use mic whenever you have questions. So yeah, that's all. Over to you, Hio.
Thank you. So I'd like to thank the organizers for inviting me to give this lecture in a conference in honor of Dani. So so today the topic of my lecture is invariant measures for horospherical flows. This is a subject Dani made a very important contribution to. So this is a general question. So let G be a connected semi-simple real algebraic group. The example we can consider is G is PSL2R or the product of PSL2Rs. So PSL2R times PSL2R or PSL-DR. Okay, and we take gamma, a discrete Zariski dense subgroup of G. Then we can form this quotient space G mod gamma. It's a homogeneous space. And we'll take N to be a maximal horospherical subgroup of G. And of course, N will act on G mod gamma by translations on the right. And our question is about, so what can you say about N-invariant ergodic measures on this space? Okay. So this is the subject of my lecture. And I'll begin with the Horocycle flow on hyperbolic surfaces. So H2 is going to be the pop space model of the hyperbolic plane. So it is just x1 comma x2 with positive x2. So we have this picture. This is just a pop space above the x1 axis. And hyperbolic metric is the Euclidean metric over the second coordinate x2. So in this model, the geometric boundary of the hyperbolic plane is this Euclidean line with a point at infinity. And topologically, it is a circle, S1. And geodesics, as well known, are vertical lines or the circles meeting the boundary orthogonally. So these are geodesics. And it is also well known that the group of all orientation preserving isometries of H2 is precisely PSL2R. So we know the PSL2R acts on this pop space in the complex plane by Möbius transformations, and that gives all the orientation preserving isometries of H2. So therefore, PSL2R also acts on the unit tangent bundle of H2, and this action is a simple transitive action, and that gives us identification of PSL2R with the unit tangent bundle T1 of H2. Okay, so every element of PSL2R we can think of with a tangent vector on the pop plane. Okay, so now if you consider this diagonal element A sub t, so e to the t over 2, 0, 0, e to the minus t over 2, then the right translation action of this diagonal element on PSL2R, this exactly corresponds to the geodesic flow on the unit tangent bundle. So if I have this unit tangent vector G, then G first of all determines the unique geodesic that it is tangent to. And I'm going to also denote by G plus the forward endpoint of the geodesic determined by this tangent vector G. Then G sub AT corresponds to a vector, which is also tangent to the same geodesic, but also with a hyperbolic distance T. Okay, so G AT, this is the geodesic flow. This is, if you flow G by the geodesic flow for time T, then this is what we get. So it corresponds to the multiplication of G with AT. And similarly, if you consider now this upper triangular matrix N sub T, 1, T, 0, 1, then the right translation action of NT on PSL2R corresponds to what's called the horocycle flow. So now for each G, we can draw this Euclidean circle, which is based at G plus. Okay, so this is called horocycle based at G plus and passing through G. And then G times NT is another vector on the same horocycle pointing to the same point, the G plus. So this is horocycle flow. And now if you have a discrete subgroup gamma of PSL2R, then gamma, action of gamma actually commutes with the horocycle flow and geodesic flow. So actually everything passes through under the quotient map. So if you have a discrete subgroup, and let's assume actually gamma is also torsion free so that we have a quotient surface. So H2 over gamma is a hyperbolic surface. And the unit tangent bundle of this hyperbolic surface is same as the unit tangent bundle of H2 mod gamma which is exactly our homogeneous space PSL2R mod gamma. Okay. And we are going to denote by N the upper triangular subgroup. So it consists of all these upper triangular subgroup N1, T01. And this is called the horocyclic group. And the right translation action of this subgroup N on this quotient PSL2R mod gamma. So this is exactly horocycle flow on the unitangent bundle of this hyperbolic surface H2 over gamma. Okay. So for this horocyclic flow, Furstenberg proved in 1973 the so-called unique ergodicity theorem, which says the following. So let gamma be a co-compact lattice of PSL2R, so meaning that the corresponding hyperbolic surface is a compact surface. Then the horocyclic action on this hyperbolic surface, in other words, this right translation action by this horocyclic subgroup on PSL2R mod gamma is so-called uniquely ergodic. And what does unique ergodic means? So uniquely ergodic means that there exists unique and invariant locally finite Borel measure on this quotient space PSL2R mod gamma. So by the way, so throughout my talk, all the measures will be assumed locally finite. Locally finite means it is finite on compact set, and it will also be assumed Borel measure. So I'm not going to repeat a locally finite Borel, but all measures will be assumed locally finite Borel measure. So again, the unique ergodicity means that there exists a unique invariant measure on the space, and since it's unique, it also has to be ergodic measure. But in this case, in PSL2R mod gamma, we know there is an invariant measure, which is namely PSL2R invariant measure. So that measure is, of course, an invariant. So in other words, Furstenberg unique ergodicity theorem says that the invariant measure on PSL2R mod gamma, in other words, is also called Haar measure. This Haar measure is the unique and invariant measure, of course, up to constant multiple. Okay, so and again, all the uniqueness are assumed to be up to constant multiple in my lecture. So this is Furstenberg's unique ergodicity theorem for horocyclic flow. Now for general semi-simple real algebraic group, so now we consider G, say general connected semi-simple real algebraic group. Again, so I'll keep actually talking about these two examples. So we can consider G, which is the product of two PSL2R. So this one has rank 2, or we can consider PSL-DR. D is any number bigger than or equal to 2, and this one has rank D-1. Now a closed subgroup N of G is called horospherical if there exists a diagonalizable element A of G such that N consists of all the elements of G, which is contracted by conjugation by A. Okay? So if N can be written as a set of all elements of G such that the limit A to the minus K, G A to the K converges to identity, then such N is called the horospherical subgroup. So again, in these two examples, for instance, so in the case when G is a product of two PSL2Rs, up to conjugation, there are 3 possible horospherical subgroups. So the first one is so product of upper triangular subgroup and the trivial group. Okay. So of course, for this group, we simply take any upper triangle, any diagonal matrix from the first PSL2R times identity. Then this N is horospherical subgroup defined by that diagonal element. And also we can switch the role of the first factor and the second factor, and then the identity times this upper triangular subgroup. This is another example of a horospherical subgroup. And lastly, we can also consider the product of 2 upper triangular subgroups. So this is also horospherical subgroup because now I can consider diagonal element, which is non-trivial in the first factor and also non-trivial in the second factor. And then that will give me this, the third horospherical subgroup. Okay. So in this case, there are 3 possible horospherical subgroups. Now in the example, G is PSL-DR. Again, up to conjugation, any horospherical subgroup is defined by these block diagonals. So we have this block diagonal matrices, identity, so D1 by D1 identity and D2 by D2 identity and so on. And then we consider the subgroup which has non-zero entries only above these block diagonals, okay, except for, of course, the ones on the diagonal. Okay? And this is a horospherical subgroup. And up to conjugation, every horospherical subgroup PSLDR is of this form. Okay, now from now on, so I'm going to denote by N. So N is going to be a maximal horospherical subgroup G. So N will always denote a maximal horospherical subgroup, and maximal horospherical subgroup is unique up to conjugation. Okay. So as we just saw, in the case of product of two PSL2Rs, any maximal horospherical subgroup is up to conjugation is the product of these full upper triangular subgroups. And in PSL-DR, again, any maximal horospherical subgroup is this full upper triangular subgroup, okay, the strict upper triangular subgroup. So maximal horospherical subgroup exists just one, like in each G of the conjugation. So extending Furstenberg's unique ergodicity for general semi-simple real algebraic group, so which proved the following result. So in 1977, so gamma is now any co-compact lattice in any connected semi-simple real algebraic group. Then again, the action of a maximal horospherical subgroup on G mod gamma is uniquely ergodic. And in other words, again, any invariant measure on G mod gamma is up to constant multiple. It is the Haar measure. So Haar measure is the only n invariant measure on G mod gamma. So this is Vich's work. Okay, so now if gamma is not a co-compact lattice, but if gamma is just lattice, non-uniform lattice, then unique ergodicity fails. So there are actually other measures which are invariant under N, which is not invariant, which is not G invariant measure. But in this case, actually, Dani gave a full classification of those N invariant measures. So here's his theorem. So in fact, actually, he proved first in 1978, when G is the product of rank 1 groups. And then in 1981, he proved this theorem for general semi-simple algebraic group. So now gamma is any lattice, so it's not necessarily co-compact lattice. Then he showed that any n invariant ergodic measure on G mod gamma is algebraic, is also called homogeneous. Okay, so meaning that, so if you denote by sigma an ergodic invariant measure for maximum horospherical subgroup, then there always exists some connected closed subgroup H, which contains N, such that this measure sigma is an H invariant measure supported on a closed H orbit in G mod gamma. Okay. So when gamma is not co-compact lattice, so sigma is not going to be generally G invariant measure, but again, it is still an H invariant measure supported on some subhomogeneous space of G mod gamma. So yeah, so this actually complete classification of Dani actually was a very important evidence for the conjecture he made. So in fact, he conjectured, I think this is maybe 1981, he conjectured actually this classification of invariant measures should be true not only for maximal horospherical subgroup, but for any unipotent subgroup. Okay. So here's his conjecture. So any invariant ergodic, so finite measure for unipotent subgroup on G mod gamma has to be homogeneous in the sense we just discussed. So it again has to be an invariant measure supported on some closed orbit of some closed group. So this conjecture was a major theoretic counterpart of Ramanujan's conjecture on orbit closures for unipotent subgroup action. And of course, so Dani's conjecture and Ramanujan's conjecture, they played very, tremendously important roles in the development of this homogeneous dynamics. And as we all know, right, so these two conjectures are proved in full generality by Marina Ratner in 1991. Okay, so, right. So in the finite volume case, we understand, all invariant ergodic measures for the action of a maximal horospherical subgroup. In fact, not only for maximal horospherical subgroup, even for unipotent subgroups. So next question is, so what can you say about n invariant measures on G mod gamma when the volume of G mod gamma is infinite? So that is when gamma is not a lattice. So I'm going to again discuss the case of PSL2R first. So let gamma be a discrete size-given subgroup PSL2R. So when gamma is another lattice, so the so-called limit set of gamma plays a very important role in the study of dynamics of this group gamma. So the limit set of gamma is defined as follows. So it is a closed subset. First of all, it is a closed subset of the boundary of H2. And formally, it is defined in the following way. So we consider some point O in H2. So O is some point in H2. And then we consider the orbit of this O under gamma. So gamma is a discrete group. So we have a countable many points. Okay, so as in this picture, we have this countably many gamma orbit. And since gamma is a discrete, so there won't be any accumulation points in H2. But then if you consider the boundary, then there will be accumulation points on the boundary. Okay. And the limit set of gamma is defined exactly the set of all accumulation points of this orbit in the boundary. This is the definition of the limit set. And if gamma is a lattice, then limit set will be everything actually. So gamma is a lattice means gamma is very big. So gamma actually goes everywhere, and then we get actually the full limit set. So limit set will be equal to the whole geometric boundary of H2, which is a circle. But in general, so limit set is a fractal set, some fractal set on the boundary. And it is known that it is also the unique gamma minimal set of the boundary. So this one can also take as a definition. So limit set is a unique gamma minimal set of the boundary. So if the limit set is not everything, then actually one cannot expect unique ergodicity result for n action, because there are many trivial n-invariant measures on SL2R mode gamma. So here's a picture. So if you have a point which is outside of the limit set, so say some point G plus, then we can consider this horocycle based at G plus. Okay, so this horocycle, because actually it is based outside of the limit set, when you consider the projection of this horocycle under this quotient map H2 goes to H2 mod gamma, so the action of gamma is not going to intervene with this horocycle, meaning that the image of this horocycle will be again some proper isometric immersion of the real line. Okay, I mean, so note that even though actually this does look like a Euclidean circle, this base point does not lie inside H2. It is in the boundary, and in fact, this horocycle is isometric to the real line R. Okay, and when the base point does not lie on the limit set, the image is again the isometric proper isometric immersion of R. So we can just simply put the Lebesgue measure on this horocycle, okay? And that gives us an invariant measure, and that's what we call this trivial n-invariant measures. So if the limit set is not everything, so there are many trivial n-invariant measures coming from the horocycles which are not based on the limit set. So therefore, we should be, if you are interested in some kind of unique ergodicity result, then we should be consider this following set. So we denote epsilon E of gamma to be the union of all horocycles based at the limit set. Okay, and this can be also written in the following way. It's the set of all G, the coset in G mod gamma, such that G plus. So G plus, remember, so G plus is exactly the forward endpoint of the geodesic determined by G, and then that belongs to lambda. Okay. So in this picture, so it's exactly, so we have this red part, which is the limit set. So take any point here, and then these are horocycles, and then this E sub gamma is simply the union of all horocycles based on limit set. And this is clearly closed and invariant subset of G mod gamma. So it is invariant under N. Okay, so now it makes sense to ask, is there unique ergodicity now for N action on this E sub gamma? Okay, so we know that, I mean, if you consider all of G mod gamma, we cannot expect unique ergodicity. So now it is reasonable to ask whether, if you restrict to this non-wandering set for N action, if there is a unique ergodicity for the N action. And the answer is yes, for class of groups which are called convex co-compact. So here's the definition. So a discrete subgroup gamma of PSL2R is called the convex co-compact. If it's convex core, if the convex core of the hyperbolic surface H2 mod gamma, which is by definition whole of the limit set divided by gamma if this is compact. Okay, but in the surface case, actually, it's much simpler. So gamma is convex or compact simply means that the corresponding hyperbolic surface has finitely many genus and also finitely many funnels. And it doesn't have any cusp. So that's what it means. It simply means the hyperbolic surface is a finite type with no cusps. In such a case, gamma is called convex compact. So now, so it's the theorem of Burger in 1990. So first, actually, Burger proved this for some special class of convex compact surfaces, and Roblan proved this in general in 2003. So if our discrete group gamma is a convex compact subgroup of PSL2R, then indeed the horocyclic action on E of gamma, so which is, again, it means the right translation action of N on this E sub gamma is indeed uniquely ergodic. Okay. So again, unique ergodic means that there is a unique N invariant measure on this E sub gamma, but when E sub gamma is not all of G gamma, it cannot be G invariant measure. So, and this measure, this unique measure is actually what is called the Burger-Robin measure. So let me now explain. So how does this Burger-Robin measure looks like? So Burger-Robin measure is defined by conformal measure, gamma conformal measure supported on the limit set. So I first have to define first have to discuss what is a conformal measure. So we have this limit set on the boundary, and Patterson and Sullivan around 1979. So they constructed the gamma conformal measure supported on the boundary. So it is, in some sense, it is simply the weak limit of some weighted counting measure on the orbit. Okay? And then when gamma is convex or compact, they showed that, in fact, this conformal measure on the boundary is unique. So therefore, actually, what they constructed, which is called the Patterson-Sullivan measure, so that is the only gamma conformal measure supported on the limit set. And that requires the assumption gamma is convex or compact. This uniqueness requires gamma is convex or compact. And now the Burger-Robin measure is a kind of product measure, which is of the form. So we can think of G as the measurable product of G mod P times P, where P is this upper triangular subgroup. Okay. So now for P, we also included the diagonals. So P is A times N. A is the diagonal, and then N was our upper triangular subgroup. And then also the G mod P is identified with the boundary of H2. So if you fix actually the point origin, then the stabilizer of origin is exactly P. So which means that actually G mod P can be identified with the boundary of H2. Okay. And on the boundary of H2, we have this limit set lying inside the boundary of H2. So I can think of this limit set times P as a subset of G. And then on this limit set, I have this gamma conformal measure, which is this Patterson-Sullivan measure. And then we just take a product with the Lebesgue measure on P. And Burger-Robin measure is the unique gamma invariant measure, which is equivalent to this product measure. Okay, of the gamma conformal measure times the Lebesgue measure on P. Okay, I mean, so to make it gamma invariant here, we have to multiply some density function over here, but I only discussed the measure class. So this Burger-Robin measure is equivalent to this product measure, which is the gamma conformal measure on the limit set times the Lebesgue measure on P, or the Hahn measure on P. Okay, and by construction, it is supported on the set of this coset G such that GP, so GP, the coset GP, so inside the G mod P, this is exactly our G plus, it's the same as G plus, and then that has to be inside the lambda because my measure is supported on lambda. Okay? So this is the Burger-Robin measure, and then again, this unique ergodicity of Burger-Robin theorem is that this measure is the unique and invariant measure supported on this E sub gamma. Okay, so the main feature of actually convex or compact groups in this unique ergodicity for n action in E sub gamma is the following property. So the limit set consists entirely of what is called the conical limit points. Okay, so what is the conical limit point? The conical limit point means this. So if Cauchy is the conical limit point, means that when you consider the geodesic ray toward the Cauchy, and this geodesic ray must accumulate on a quotient surface. Okay? So any geodesic ray toward the Cauchy is recurrent to a compact subset in the surface. That's what exactly means that Cauchy is the conical limit points. So indeed, actually, lambda is equal to the conical limit points. This is the equivalent definition of gamma being convex or compact. So this is actually the main feature of a convex or compact group, which is relevant to this unique ergodicity question. In other words, we can actually rewrite, we can reconsider this E sub gamma as the recurrent set of the geodesic flow. Okay? So formally, we can think of the recurrent set as the set of points when you flow by the geodesic flow. So G, remember, so G times AT is the geodesic flow. And when you flow the this tangent vector or G by the geodesic flow, if it accumulates, meaning that the lim sup of this gamma GAT is non-empty, then we say this G is a recurrent point for the geodesic flow. And for convex or compact group, so this property that limit set is same as the conical limit set says that E sub gamma, so non-wandering set for the n action is exactly equal to the recurrent set for the geodesic flow. Okay. So in fact, actually, using this, this property also holds for any rank 1 group. So it's a theorem now by Roblan and Winter that in any semi-simple real algebraic group of rank 1, so there's a notion of convex or compact group, and if gamma is convex or compact, then n action on E sub gamma is uniquely ergodic. Okay. So it's very same, like we have again the unique gamma conformal measure on the boundary, and then one defines the Burger-Robin measure, and then using this recurrence property, they can show that actually n action, this Burger-Robin measure is the unique and invariant measure supported on this set E sub gamma. Okay, so now we go to the higher rank case. Okay, so now, so in the higher rank case, so let G be now general connected semi-simple real algebraic group, and then let gamma be a discrete Zariski dense subgroup. And as in the PSL2R case, so very important notion in the study of the dynamics on G mod gamma or gamma is something called the limit set of gamma. So now I want to define actually, so what we call the limit set of gamma, and then for that we need to pick some notations. So we are going to denote by P a minimal parabolic subgroup of G. So the P is the minimal parabolic subgroup is the same to say that P is the normalizer of maximal horospherical subgroup. So this is my relation between maximal horospherical subgroup and minimal parabolic subgroup. So in other words, actually, so this P has so-called Lagrange decomposition, M times A times N, where N is again my maximal horospherical subgroup, and A is a maximal real spirit torus, which of course normalizes N. And M is a compact group which centralizes A. Okay? And of course, since A is the maximal real spirit torus, so dimension of the Lie algebra of A is exactly the rank of G. So for a minimal parabolic subgroup, this quotient G mod P, this is called the Furstenberg boundary of the symmetric space G mod K. Okay? This F is called Furstenberg boundary. So I also use this Cartan decomposition. So, Cartan decomposition says that G can be written as K times exponential of some positive Weyl chamber A plus and K. So A plus is the positive Weyl chamber in the Lie algebra of A. And this Cartan decomposition let us actually define what is called Cartan projection map. So Cartan projection map is a map from G to this positive Weyl chamber A plus such that we map G to mu of G so that mu of G is the unique element in A plus such that G belongs to the double coset of exponential mu G by K. Okay, so there is a unique element. So this in this Cartan decomposition, this A plus part is always uniquely determined, and then that A plus part is the Cartan projection of the element. So in the rank 1 case, the Cartan projection is nothing but the distance from a point to K. So in the symmetric space of G mod K, you can think of the distance between G sub K, GK, and K, and Cartan projection is precisely this distance in the rank 1 case. So in higher rank cases, so Cartan projection, we can think of it as some kind of vector valued distance. Okay, so of course the image, so this is an element in A plus, so it is a vector. So we can think of Cartan projection as a vector valued distance function. Again, here is the example. So in the case when G is product of two PSL2Rs, so product of two PSL2R is the same as the identity component of isometry of the Riemannian product of two hyperbolic planes, H2 times H2. So in this case, our P, minimal parabolic subgroup, or the normalized of our N, which was upper triangular subgroup, is now again this upper triangular subgroup, but this time containing the diagonals. Okay, and A is of course this two-dimensional diagonal group. We have the diagonal group from the first component and second component. And the G mod P, the Furstenberg boundary in this case, it is the product of two boundaries of H2. So it's the boundary of H2 times boundary of H2. Okay, so here is important to note that actually this Furstenberg boundary is not same as the geometric boundary of this Riemannian symmetric space H2 times H2. Okay, so to this product group, the corresponding Riemannian symmetric space is the product of two H2, but the geometric boundary is boundary of H2 times all of H2 union, all of H2 times boundary of H2 union, and Furstenberg boundary. So geometric boundary is much bigger, okay? But the Furstenberg boundary is in some sense the smallest boundary component, okay? And the positive Weyl chamber in this case, so the Lie algebra of A can be identified with R2, just to we send these 2 points to T1, T2. So the Lie algebra A is simply R2, and then A plus. The positive Weyl chamber is simply this first quadrant in R2. So in the second example, G is PSLDR. So the normalized of the upper triangular group is again this upper triangular group, but containing the diagonals, and A is this diagonal subgroup. And the Furstenberg boundary G mod P is now space of full flex on this Euclidean space R to the D. And A plus is again this cone inside the Lie algebra of A. Okay, so now I'm ready to define what is a limit set. So limit set of discrete group gamma of G, this will be a complex subset of the Furstenberg boundary. Okay, so it will be always complex subset of Furstenberg boundary. And here is how we can think of. So G mod K is the corresponding symmetric space. So take any point in the G mod K, and then just like what we did in H2 case, we look at the orbit gamma O, and then we have a countably many discrete subset in G mod K, and they will accumulate on the boundary, on the geometric boundary. Okay, but we'll only collect those points which accumulate on the Furstenberg boundary, and that will be the limit set. Okay, so we simply take all the accumulation points of the orbit which lies in the Furstenberg boundary, and then that is our limit set. And it is known that, so remember, actually, I am assuming gamma is Zariski density. It's very important assumption. And under this condition, it is always the unique gamma minimal subset of the Furstenberg boundary. So one can also take that as a definition of the minimal set. So unique gamma minimal subset of the Furstenberg boundary. Okay, then similarly as before, we can define E sub gamma exactly in the same way. So it's a set of all coset G mod gamma such that GP, so now this coset GP lies in lambda. Okay, so I have this map, the projection map from G to G mod P. G goes to simply GP, And then the limit set is a subset of G mod P. So this condition makes sense. And this is exactly the same set, which generalized E sub gamma we defined for PSL2R before. And because our limit set is the unique gamma minimal subset of F, this E sub gamma is unique P minimal subset of G mod gamma. Okay? So now inside this E sub gamma, we have actually family of what we call directional recurrent subset. So in the rank 1 case, we talked about recurrent set under the geodesic flow. But in higher rank case, we have many directions, not only one direction, because the diagonal group has the dimension which is same as the rank of G. So for each vector V in the positive Weil chamber, we'll consider this what we call V-directional recurrent subset. And the notation is RV. Of course, R stands for recurrent here. So R sub V is the set of elements in G mod gamma such that when you flow by exponential TV, so this is the diagonal, one-dimensional diagonal flow in the direction of V, okay? And then if there is an accumulation point of this flow, then we call that element belongs to this V-directional recurrent set. Okay, so it's very much the same as the recurrent set for the geodesic flow, except that instead of geodesic flow, we have many directional flow in higher rank. So we look at for each V in the positive Weil chamber, we look at that directional flow, and then if there is an accumulation point, then we collect those base point. That is the V-directional recurrent set. So it's easy to check this is a P-invariant set, but it's not in general closed set, but it is a P-invariant Borel subset of E sub gamma. But note that, so for instance, if gamma is a co-compact lattice of G, then of course G mod gamma is compact, which means that every point is recurrent under any directional flow. So in that case, R of V for any V will be same as G mod gamma. So all the recurrent set will be simply G mod gamma if gamma is co-compact. But in general, actually, this can be quite mysterious then. How do you know when the point comes back under some direction and then maybe it doesn't come back on the other direction? Okay, it's not obvious at all how this set looks like. But however, analogous to the actually convex compact case in the rank 1, we could ask, if you just look at this recurrent set, which is a P-invariant Borel subset, is there a unique ergodicity for the action of maximum Horospherical subgroup for certain class of discrete subgroups? Okay. So for convex or compact groups, in the rank 1 case, we know that this R of V was exactly equal to the E sub gamma, and then there was a unique ergodicity. So we want to ask if there's a higher rank analog of this phenomenon if you look at the V-directional recurrent set. And the answer is yes, actually, for some cases. And now I want to define what is called Anasov subgroup. So to define this Anasov subgroup, I fixed the set of simple roots. So alpha 1 to alpha R. So that means that R is exactly the rank of G. So fixing this set of simple roots gives me a coordinate for the Lie algebra of A. So I can map any element to U in the Lie algebra of A to alpha 1 U and all the way up to alpha R U. And so that gives the vector space isomorphism between A and then the R to the rank of G. So in other words, it is precisely actually, I'm giving the coordinate system to the Lie algebra of A. Okay. Now, a finitely generated subgroup gamma of G is called Anasov. So with respect to set of all the simple roots, if we have the quasi-isometry between two spaces. So we consider gamma with respect to the word metric. So because it's a finitely generated group, so I can fix some finite generating set and then we can consider word metric. And then another space here is that, so this is not in general is a metric, but it's going to be actually pseudometric. So then we can think of, we can actually put the ith component of the Cartan projection to gamma. Okay, so this notation mu is the Cartan projection, and then I compose with alpha I, which means that it's like the ith component of the Cartan projection. And for every I, if we have a quasi-isometry between these two, then group gamma is Anasov. Okay, so by quasi-isometry, this is what we mean. So there are some constants C1 and C2, such that for every gamma in gamma, so when you consider this alpha I mu gamma, so this is what I'm looking at. So alpha I composed by mu. So alpha I mu gamma has to be bigger than equal to, say, C1 inverse times the word length of gamma minus C2. So of course, in the definition of quasi-isometry, we have an upper bound and a lower bound, but in this case, actually, upper bound holds trivially. So upper bound is not important, but the point is about the lower bound. Okay. So if the finite generated group actually satisfies this property, then we call it Anosov. So first, let me mention that, so this notion of Anosov groups were introduced by Laborie in 2006 for surface groups. And then Ghosh and Wiener generalized this notion for word hyperbolic groups in 2012. And then by now, actually, there are many equivalent definitions of these Anosov groups. And this definition I gave you, I think this is due to Kapovich and then Lip and Porty. Okay, so this is one of the equivalent definitions of Anosov groups. So I like this definition because it gives somehow more geometric meaning about the group. So in the rank 1 case, so what does this condition mean? In the rank 1 case, so Anosov exactly means that gamma, given the word metric, is quasi-isometric to the orbit of gamma with respect to the Riemannian metric. Okay, so you fix some O, which is a point in the symmetric space G mod gamma, and then we can restrict the Riemannian metric to the orbit of gamma O. Okay, and then this is a metric space because I just restricted the Riemannian metric to the orbit. And in the rank 1 case, so the Cartan projection is simply the distance function, and then there's only one simple root. So this Anosov condition precisely means that gamma is quasi-isometric to the word metric. And this is a well-known equivalent condition to the convex compactness of group. Okay. So in other words, in the rank 1 case, Anosov groups are precisely convex compact groups. So here's a little cartoon. So if you have a co-compact lattices in rank 1 group, and then they are special class of convex compact groups in rank 1 space. Okay, and as I just said, so in rank 1, Anosov groups are precisely convex compact groups. Okay. But in higher rank, so as we all know, like by Margulis arithmetic theorem, in higher rank, all irreducible lattices are arithmetic. So therefore, there are only countably many lattices of the conjugation. So we have this only countably many, these isolated, say, lattices in the space of all discrete groups. But Anosov groups are very big. It's huge. And in particular, if you have an Anosov group, then a small deformation is again an Anosov group. So it is open family. And it contains some of the very nice explicit families, such as Schottky groups and Hitchin subgroups. So these are actually groups which were studied by Laborie. And also something called the self-joining groups. So it contains this huge family of groups. And I will talk a little bit more about self-joining groups because it will be important for the later part of my talk. So what do I mean by the self-joining group? So here's the first example. So take any co-compact lattice of PSL2R. And if you have an element in the Teichmüller space of the corresponding surface, closed surface, that means I have some discrete phase representation of gamma into PSL2R. Okay, so for every element in the Teichmüller space, so there is a discrete phase representation of gamma to PSL2R. So then using this representation, I can actually, sorry, this has to be not gamma, but sigma. And this has to be also sigma here. Okay, so then we can actually embed, we can put actually sigma into the product of two PSL2Rs using this representation diagonally. Okay, so by self-joining of sigma via rho, this is what we mean. So identity times rho sigma is the group consisting of G comma rho G and G is from sigma. Okay? And this is clearly subgroup of PSL2R times PSL2R, and it is a discrete subgroup. But really the way to think about is that, so we put in discrete subgroup sigma of PSL2R to the product diagonally using some other representation of sigma. Okay, so the groups obtained this way will be calling them self-joinings, because you start with the sigma and then you somehow join this sigma using the representation with itself, and then put it in the product group. Okay? And it's easy to check actually these groups are Anasov groups, because I just said that the in the rank 1 case, the Anasov groups are convex or compact groups, and here each just the projection map gives the simple row. So it's easy to see actually these are Anasov groups. More generally, we know actually completely how Anasov groups in the product of rank 1 groups look like. So this is a statement. So consider the product of rank 1 simple algebraic groups. G is the product of GI, and then so suppose the rank of GI is equal to 1. Okay. Then Anasov groups in the product of rank 1 groups are always obtained as self-joinings of some convex or compact groups. More precisely, let sigma be any finitely generated group, and now rho I be a convex or compact representation of sigma to GI with finite kernel. Okay? So convex or compact representation means that the image is a convex or compact subgroup of GI. Okay? And then we also assume that the representation has finite kernel. Then again, I can embed actually, I can put sigma into the product of GIs via these representations. So that's what we call self-joining. It's a product rho I and sigma. So meaning that element of gamma consists of just diagonal embedding of sigma into the product of GI. And again, it's easy to check these Anasov groups. And also any Anasov group in the product of rank 1 arises this way. So we know completely what Anasov groups in the product of rank 1 groups are. Okay, so now, so how does now higher rank analog of Burger-Robin measure look like? Okay, so they look very similar. So again, I'm writing G as the measurable product of G mod P times P. And then in G mod P, which is Furstenberg boundary, so there's a limit set. So we define the limit set as the gamma minimal set in G mod P. So now, if you have a gamma conformal measure on the limit set, so then the Burger-Robin measure will be again a gamma invariant measure, which is equivalent to the product of some gamma conformal measure on the limit set times the Haar measure on P. Okay, so it looks exactly the same as the rank 1 case. But the question is, we need to understand what are gamma conformal measures on the limit set in this higher rank case. And understanding that is related to also the notion of the limit cone. So the limit cone of gamma, so this is the subcone of the positive Weyl chamber of A plus. So it is defined as the asymptotic cone of the Cartan projection of gamma. Okay, so remember, so for every element of gamma, Cartan projection gives you this A plus part. So we have discountably many points which are Cartan projection of gamma, okay, in A plus. And the limit cone is simply the union of all the directions, asymptotic directions of this Cartan projection of gamma. Okay, that is exactly what is called asymptotic cone of mu gamma. And formally, it is the limit of all Ti times mu gamma I for sequence Ti going to 0, and gamma I should be, of course, from gamma. So you can think of it as kind of union of all the limiting directions. And it's not obvious at all, but when gamma is Zariski dense, actually the limit set is a convex cone. It is a convex cone with a non-empty interior. So this is the theorem of Bonua in 97. So because it has non-empty interior, so we have many directions. So we have actually the rank of G family of directions in the interior of L. And for every direction in the interior of L, or for any unit vector in the interior of L, Kang constructed a gamma conformal measure corresponding to this direction supported on the limit set. Okay? So it's a generalization of this Patterson-Sullivan's construction. But for every direction, he constructs this. So we get this map. So this is the space of directions in the interior of L. And then for each direction or for each unit vector in the interior of L, we have a gamma conformal measure on the support of which is supported on the limit set. Okay? So, okay, in general, okay, so we have this map, but we don't know whether it's injective or surjective. So for instance, if gamma is co-compact lattice, of course, co-compact lattice is also discrete arithmetic dense group. And this construction gives you a Lebesgue measure on G mod P on the Furstenberg boundary. Okay, so when gamma is if gamma is convex or compact, actually, then all of this measure becomes the same measure, which is simply the Lebesgue measure on the Furstenberg boundary. Okay. So, okay, so now from now on, for the rest of my talk, I'm going to assume gamma is Anasov and Zariski dense. So gamma is or Anasov. In the case, actually, gamma is Anasov. In fact, actually, this map, this U goes to this conformal measure corresponding U. This turns out to be, in fact, bijective. So we get actually classification of all conformal measures. So this was proved with Minju Lee in 2020. So again, like for every direction in the interior of L, we have one gamma conformal measure. But what it proved is that in the Anasov case, it is a bijection. So, and moreover, actually, if you have two different directions, then the measures not only they are different, but in fact they are mutually singular to each other. And every gamma conformal measure on lambda is obtained in this way, is obtained by that construction. Okay. So therefore, we have actually family of gamma conformal measure, which is homeomorphic. So we also prove they are not only bijective, but they are homeomorphic. So we have actually here family of gamma conformal measures, which is parameterized by R to the rank G minus 1. So this is compatible to the rank 1 case, because in the rank 1, we said gamma is convex or compact, and in the rank 1, this is simply point. So this recovers the uniqueness of gamma conformal measure proved by Patterson-Sullivan. And in the Anasov case, we have exactly this family parameterized by the interior of the limit. Okay, so again, so whenever, so therefore, actually, for Anasov case, we also get the family of these Burger-Robin measures for each direction in the interior of the limit, and which are also mutually singular to each other. Because, yeah, these conformal measures are singular to each other. Sorry. So therefore, the corresponding Burger-Robin measures are singular to each other. And so we get this P quasi-invariant measure, which is supported in E of gamma. So with the Minju, actually, we also proved the ergodicity of this Burger-Robin measure. So this is a P quasi-invariant and N-invariant measure. So the first question we had was that if this measure was ergodic, so we wanted to understand the ergodicity, and we proved that for every U in the interior of L, each of these Burger-Robin measure is ergodic for the action of M times N. Remember, so M is this compact group which centralizes A. Okay, so it is ergodic if you look at M times N, the compact extension of maximum Horospherical group. But in general, if M is not connected, which is same as if P is not connected, then this measure may not be ergodic for N action. We cannot simply remove M unless M is actually connected. But we nevertheless actually we understand precisely the ergodic decomposition and ergodic decomposition of this measure. So what it proves is that there is this constant K depending only on gamma, which is between 1 and then the connected components of P. There are precisely K number of N ergodic components for this Burger-Robin measures, independent of U. Okay, so we have complete understanding about the N ergodic components. So in particular, this theorem says that if M is connected, so this is always case if you consider the product of rank 1 groups, which is center free. In that case, the Burger-Robin measure is also ergodic for N. Okay, so this answers the ergodicity question for Burger-Robin measure. So so remember, so we were interested on the unique ergodicity question on the recurrent set, for the directional recurrent set. So let me remind you the definition of a directional recurrent set. For every direction in the positive Weyl chamber, we could consider this a directional recurrent set under that direction, which was a P-invariant Borel subset. Then it was a natural question for us to understand what is the relation between this Burger-Robin measure for the direction U and then the U directional recurrent set. And there is actually, and we found actually there's a surprising rank dichotomy for this relation. And so this was proved jointly with Mark Berger or Landesberg-Lee last year. So if the rank of G is at most 3, so if the rank of G is 1 or 2 or 3, then for any U in the interior of L, the Burger-Robin measure is fully supported on this U directional recurrent set. So in other words, this U directional recurrent set is corner for the Burger-Robin measure. Okay, so meaning that the complement of RU has measure 0. Okay, for this Burger-Robin measure, and in all other cases, meaning that either rank of G is at least 4, or you look at the direction which does not belong to the interior of L, or you look at the direction which is different from U, then the V directional recurrent set is a null set for the Burger-Robin measure. Okay. So this rank dichotomy was a surprising result. And then finally, we now have this unique ergodicity result, so which answers our initial question. So this was the joint work with Landesberg-Lee and Lindenstrauss last year. So for this theorem, now I have to restrict to the product of rank 1 groups. Okay. So far, all the discussion was about actually general semi-simple real algebraic group, but for this last theorem, we restricted to the product of rank 1 groups, even though I don't think actually we should really have this restriction, but that's what we proved. So consider the product of rank 1 groups. So it is the product of, say, GI and then R number of rank 1 groups. So R is going to be exactly the rank of G. And I mean, so far, of course, I was all the time assuming gamma is anisotropy, but then since I'm now considering the product of rank 1 groups, I can be more specific. So gamma is exactly this self-joining of convex or compact groups. Then if the rank is at most 3, so if the rank is 1 or 2 or 3, so for instance, you can consider the case G is the product of 2 PSL2R or the product of 3 PSL2Rs. Okay, so in that case, for every direction in the interior of L, we consider this U directional recurrent set, and we have a unique ergodicity for the maximum Horospherical group action. More precisely, this Burger-Robin measure in the direction U, this is the unique N-invariant measure, which is supported on this directional recurrent set. And otherwise, either rank is at least 4 or the direction does not belong to the interior of limit cone. In that case, there is no invariant measure supported on this U directional recurrent set. So directional recurrent set in that case does not support any maximal Horospherical invariant measure. Okay, I think I'm exactly on time. So happy birthday, Dani.
Yeah, questions for the speaker?
Hi, this is Uri Shapira.
Oh, hi.
How are you?
Good.
So,
it's 11:30. What do you expect? 11:30 p.m. for me. Okay.
Yeah, it's nice to hear a talk. So a few slides ago, you mentioned the dichotomy. I think one, yeah, and I just didn't get it. So can you explain again what's going on with the two items in the theorem?
Right. So I have a directional recurrent set for each. So I have for each direction. So we can consider directional recurrent set. And then for each direction, I also defined the Burger-Robin measure in that direction, right?
Yes. So
this theorem says that. Okay, let's just think about the product of PSL2Rs. So if we look at the product of PSL2Rs up to factor 3, then this Burger-Robin measure is fully supported on the directional recurrent set.
Okay. The first bullet
so
I got
this
it.
is like exactly, so in the rank 1 case, this is exactly the BR measure is supported on E sub gamma. This is just nothing but like that. But surprisingly, but now if you look at the higher rank meaning not just bigger than 2, but bigger than 4, then this Burger-Robin measure we defined actually it is, of course, by definition, it is supported on this E, but however, it gives the measure 0 on the directional recurrent set. So in fact, even though I stated this statement in terms of Burger-Robin measure, it is the same statement. You can look at the this gamma conformal measure, and one can also state this theorem in terms of this gamma conformal measure. So we have this family of Patterson-Sullivan measures for each direction, but this recurrent set for each direction is very, very small in very higher rank case, if rank is bigger than 4, and then this somehow directional conical set is measure 0. That's what it says.
I think just logically, I had trouble absorbing the second bullet. So you're saying, if I'm assuming the rank is at least 4, then
yeah.
RU is actually a null set for the Burger-Robin measure of U?
Right. So among the limit set, there are limit sets which is the recurrent for certain direction. But since this is a higher rank, actually, if you consider all of A, it can be recurrent, but it does not have to be recurrent when I fix the direction, right? There's a huge difference.
Mm-hmm.
So in the Anasov case, if I look at the full A, this higher rank A, then it is also true the limit set consists of the conical limit points for the action of full A, like this, okay? But now I'm not looking at full A, I am looking at one-dimensional flow. So recurrent for the full A, of course, does not mean that you are recurrent for a fixed direction, right? Because you can be recurrent like this.
Yes.
So it is that difference. If you look at full A, then in Anasov case, every point is recurrent for the full A. But if you fix the direction, then there is this surprising difference. If you look at up to rank 3, then there are many recurrent points, meaning that actually gamma conformal measure, it has a full Patterson-Sullivan measure. But in higher rank, the recurrent points are very sparse. So this Patterson-Sullivan measure does not see it is measure 0 for the Patterson-Sullivan measures. That's what it says.
Okay, thank you.
Does it make sense? Yeah.
Yeah, thanks.
Hello. I have a question about the number of ergodic components of the Burger-Robin measure for any direction. So I find it a bit mysterious or curious why this number does not depend on U. Could you maybe say a few more words about it?
Right. So this number K, so there is a subgroup of M, normal subgroup of N, which contains the connected component. So connected component M, which determines actually this K. And then this normal subgroup of M, these are in some sense basically all the Jordan. So there is a notion of Jordan projection of loxodromic element, which gives the element of A, but there's a generalized Jordan projection, which also captures not only the A part, but also this M part. And then in some sense, this subgroup is the closed subgroup generated by all these Jordan projections of the element of gamma into M part. So it only depends on gamma, but of course it is a theorem. So when we first proved this theorem, we couldn't say actually this number does not depend on U. We could only say there are finitely many, but then of course we had to prove it. So our proof says that in fact actually this number, no matter what U is actually, you only see actually, this index of this normal subgroup inside M. So that is exactly the number of N ergodic components. Yeah.
Okay. And can we say anything about the case in which the index is realized?
Yes. For instance, for this what's called the hitching component, for those actually, this M naught is in this hitching component groups. So these hitching representations go into PSL DR. So in that case, what is M? M is simply this finite group, which consists of plus minus ones in the diagonal group. It's a finite group, but this the normal subgroup I was mentioning, it is known to be a trivial group. In that case, actually, this K is exactly the cardinality of this finite group. So it is known in that case what this number is, right? So in the lattice case, actually, this normal subgroup will be all of M, so you don't see it. So of course, in the lattice case, the BR measure is simply Haar measure, and we know the Haar measure is ergodic for any non-compact closed subgroup, right? But in the non-lattice case, it's not one in general. And then, for instance, for Hitchin representation case, it is exactly the full cardinality of this finite group.
Okay, thank you.
Are there any more questions? Okay, if not, let's thank the speaker again.
Thank you, and happy birthday, Dani, again.
Thank you very much.